Okay, so now before we go to the equations for a fluid, the full equations for the momentum equations for a fluid, I want to back up a little bit and just review Newton's law. And by way of review, yet not having only review, I'm going to derive Newton's laws from the idea of conservation of energy, right? So probably in your mechanics class, maybe you saw that if you write down Newton's law, you can derive a conservation of energy principle. But you can also go the other way around, postulate the idea that energy is conserved and derive Newton's law. So I'm going to work the other way around. So there's something a little bit new for the lecture for some of you. All right, so what is the energy E, right, in a mechanical system? Usually we talk about two types of energy, the kinetic energy and the potential energy. So the kinetic energy is going to be 1/2 mv squared, the velocity squared. And I'm going to write it like this, v dotted with v. And that's the kinetic energy. Well, let me take two steps. Is E kinetic plus E potential, and E kinetic is equal to 1/2 mv, that's the velocity, dot v, right? So 1/2 mv squared, and v squared, remember, that's the speed squared. So if I do v dotted with v, that is going to be Vx, Vy, Vz, or even better, if I use the usual notation we use in fluid dynamics, for the three components of V, I'm going to write a U, V, and W. Dotted with itself, dotted with U, V, and W. And if I take the dot product, that will be U squared plus V squared plus W squared, right? Which is just the square of the speed, right? Remember the speed, V, which is equal to the magnitude of V. Now I'm using V again, curly V, the speed. Which letter should I use? What should I use? The speed, I'll just write speed.
Yes.
Speed is equal to the magnitude of V, is just the square root of U squared plus V squared plus W squared. So when I do the 1/2 mv squared, it gets rid of the square root. So this is consistent, all right? E dot V. It's not mysterious. Okay, so that's the kinetic energy. And then I also need a potential energy, E potential. And I'm going to write that just as a potential, V, capital V. And that's going to be a function of position of R. All right? Okay, so then, to do the energy conservation, what I need to do is do dE, dt, and use the fact that that's zero, right? Energy is conserved, so that is equal to 0. So I'm going to sub in what E is using these two EK plus EP. That gives me d by dt of E kinetic plus E potential, which is now equal to d by dt of 1/2 mv dot v plus v of position r, and this is the potential. All right, so now I'm going to do the calculus. I'm going to use the product rule on this term and the chain rule on this one. All right, so let me show you what we get. So the first term, v, right, is a function of time. So I'll get 1/2 m dv dt dotted with v plus 1/2 m v dotted with dv dt, right? That's just the product rule. So this is equal to this. That's the derivative of the first term, plus. And then you look at this one and you might say, well, this is not a function of time, so dv dt is 0. But this is the derivative of v, and through the chain rule, we have to use the fact that the position is the position of the particle we're thinking about, or the mass, and it is a function of time because it has a velocity. So we have to use the chain rule. So we'll do plus dv, or grad v, right? The gradient of v, we'll do a dv dx times dx dt, right? Plus dv dy, dt. And so what we're left with is grad v dotted with d by dt of the position, r. Right, so that's the chain rule, recognizing that v here is a vector. So when I use the chain rule, I have to differentiate the three components of v, the x, y, and z components in Cartesian. And then using the chain rule, I end up with a dot of dr dt. And so this then becomes equal to, these two terms are the same, right? A dot b and b dot a are the same thing. So this is the same term. So the two halves become one. So I have m v dotted with dv dt plus, and this term dr dt, well, the rate of change of the position is just the velocity. So this becomes v dotted with grad v, where v is the potential energy, remember. And then I can group these two terms. This becomes m, or no, it becomes, I'll pull out the v dot v dotted with m dv dt plus grad v. And remember this whole thing here, I start off by taking the derivative of the energy, right? And so this whole thing now has to be equal to 0 because the energy is conserved, right? The e dt was 0. And now v here, right, that's the velocity of the particle. I could give it in any old initial condition, and this equation still has to be true. So v is arbitrary, right, because I could start off the particle at any velocity I want, yet it has to satisfy this equation by energy conservation. So the only way that this can be 0, always for any v, is if this term is 0, right? Because if we just think that this just means these two vector quantities are perpendicular, that's fine if we pick v in one direction. But now if we change the direction of v, it would mean it's still perpendicular. That can't be true unless the quantity in parenthesis is equal to 0. And so this means that m dv dt is equal to minus grad v, right? And this is Newton's law, right? So grad v is the force, right? So the gradient of the potential gives us the force. So is equal to m dv dt, right? dv dt is the acceleration, ma equals the force, where the force is given by the gradient of the potential. Or minus the gradient of the potential. So we have the potential, we take its gradient, we go in the negative direction, we get the F. So if we think of gravitational potential energy, right, that's the way it works, right? If you put a ball high up above the ground, it's in a region of high potential energy, and the force will be downwards, will bring it towards the center of the earth where the potential energy is less. So this force here that goes like minus the gradient of the potential has the same form as the pressure force, right? Remember from the last lecture, the pressure force was minus gradient of P, right? So in mechanics, the force is minus the gradient of the potential. All right, so that's that for the second lecture. We reviewed Newton's law, and we went about it by starting off with conservation of energy, and from there we derived Newton's law, using the fact that we have a conservative force which can be written as minus the gradient of a potential.